So welcome, I'm gonna present you a new Coreset framework for clustering, which is a joint work with Vincent Cohen-Haddad and Chris Spiegelsen, and I am David Solvik. To break down briefly the title, a Coreset is a data compression scheme, and so we want to do data compression for clustering problems. So more precisely, we are targeting center-based clustering problem. The input is a set of points here, and the goal is to find a set of k-centers, such as, so the red dot, such as to minimize the sum of distances to the closest red center, or sum of distances square, or more generally, sum of distances raised to the power z. Okay, so this problem encapsulates the classical k-median objective function, where the objective function is simply the sum of distances to the closest point of C. For instance, in that example, the point that minimizes the cost function is the red point. It also encapsulates the k-center problem when z goes to infinity. Here the goal is to minimize the maximal distance to the closest point in C. And the k-means problem where the cost function is the sum of squared distances. So in that talk, think about that case, z equals 1. The cost function is simply the sum of distances to the closest center. Okay, and as I said, we want to compress the data set. So for instance, in that case, where you have a pretty clear clustering, if you wanted to compress the dataset, it would be enough to take few representative points in each cluster, that way, taking few points in each of the cluster. This represents quite well the dataset. Each cluster has like 3 points. Okay, this is representative enough. So if we have a clear clustering, then we can represent well the dataset by picking few points in each of the cluster. The other extreme case is when there's no clear clustering at all, the dataset is random. Then we can use the randomness to pick few random points and say that, okay, this is representative of the dataset because I picked random points in a random dataset, so it will have good statistical property. So the question is, what do I mean exactly by to represent a dataset? And that's what Coreset formalizes. So the definition of a Coreset is as follows. We are given a set of points A, the green point, and we say that a subset omega with weight is a Coreset if for all set of centers, for instance those 2 blue points, the weighted cost of omega to the solution S is roughly equal to the cost of A to solution S. So that means that the sum of the distances from the green point to the blue point is roughly equal to the weighted cost of the red point to the blue point. So weighted means that this distance counts 4, this distance counts 2, and this distance counts 5 times. So we want that the sum of the green distance is roughly equal to the sum of the red distance. And that needs to hold for any set of blue centers. So it has to hold for those 2 blue centers, but also for those 2. They are pretty different, but we still want that the sum of the green distances, the distances from green point to blue, is equal to the weighted sum of the red point to blue. So this is the object we're considering in the talk. So the goal is to construct a Coreset, show that it exists, consisting of as few points as possible. Of course, we want to build the Coreset as fast as possible and ideally as simply as possible. So that's our goal. We want to build a Coreset, so something that represents the dataset with as few points as possible and build it ideally fast and simply. So the state of the art for Coreset construction is as follows. It has been introduced in the Euclidean spaces by Harpeld and Mazumdar back in the time where the dimension was small, so being exponential in dimension was okay. The first breakthrough is due to K. Chen, who presented a Coreset construction with dependency linear in D. So we'll see afterwards how he managed to do that. Then maybe the other most important work is the Feldman and Lemberg result, who designed a framework relating Coreset construction to VC dimension. And that framework was used by all the subsequent paper here to build Coresets. So the last result is the best for Euclidean spaces is k log square k due to Huang and Vishnoi, last STOC. And what we present here is a new framework, so we get rid of the VC dimension techniques, and that in Euclidean space slightly improves what was known before, so we shave a log k. Most importantly, the dependency in Z was 2Z, while we have only a single Z. So for Z equals 2, we have epsilon to the minus 4. For Z equals 3, we have epsilon to the minus 6, etc. While they had 6 already for Z equals 2. Anyway, that's not the most improvement. So Coreset do not exist only for Euclidean spaces. You can have Coresets for finite metrics, doubling metrics, whatever. On all those metrics, all the previous work was due to the Feldman-Lemberg framework. In doubling metrics, it's an application of that framework that led to Coresets of size k cube. In bounded truth graph, same framework. In minor free graph, variation on the same framework. So what we managed to show is that our framework improves on all those results simultaneously. So we have polynomial improvement in doubling metrics, graph with bounded true width, and minor free graphs. And we claim that our framework is simpler to apply than the Feldman and Lemberg one. And we'll see why and what do you need to apply it afterwards. Okay. So that's it for our claims. Now, why are Coreset important? So first, it's a very nice structural tool. If we think of it, we show that there exist Coresets of size independent of n. So it means that if you want to solve k-means for k equal 10, so you want to find 10 clusters, and you want to evaluate the cost of any solution to those consisting of 10 clusters, you want to just to evaluate the cost. Then we claim that you need only a couple of 100 points to have precision 1%. Whatever the input size is, you can have the input size could be of size 1 billion, you would need the Coreset of size, say 200. If it was 200 billions instead of 1 billion, the Coreset size would still be 200. And 200 would be enough to approximate the cost of any solution with 10 clusters. So that's very impressive to me. Then other contribution of the Coreset field is that it speeds up the running time of algorithm. If you want to compute best k-means solution, you have an algorithm in T, and then if you run it on a Coreset, you have running time dependent on the size of the Coreset only. And it applies to memory constraint settings. So if you have small memory, then you start by computing a Coreset, and then you can do whatever you want because it's a data compression scheme. So that's the point. Okay, so now our contribution for Coreset analysis is that we present a new framework, arguably easier to apply than the Feldman-Lamberg framework, that allows us to improve on all previous Coreset bounds, as I shown. And we canonize Coreset constructions to very simple and structured inputs. So before, the Coreset construction algorithms were very simple. It was sample delta points according to a simple distribution. And then the bulk of the work was the proof, the analysis of the algorithm. We have a slightly more complicated algorithm where we divide the inputs into those very simple and structured inputs. And on those inputs, then the proof is simpler. So we have an algorithm that's slightly more complicated, but that allows us to simplify a lot the proofs. Okay, we'll see what those simple and structured inputs are in a moment. So that's our contribution. Now the plan for the talk is as follows. I'm going to present that very simple case and the sketch of proof for it. And then we'll see how to generalize. The proof strategy is as follows. First, record the definition of a Coreset. We're given a set of point A. We want to compute a weighted subset of A, such that for all sets of K-center, the cost is roughly preserved. So what we'll do is that we're going to find a distribution D, such that if we sample delta points from that distribution, we have for any fixed solution that the cost is preserved. So instead of having the guarantee for any set of center, we have it for a fixed one with some huge probability. So then, if we manage to have that, we just need to do a union bound over all solutions to say that the sample we have, omega, is the Coreset for all solutions. That's not as easy as it sounds, because there may be infinitely many possible solutions. For instance, in the plane, even for k equals 1, there's infinitely many possible center. Okay. So how to do the first point? So start by doing some assumptions. We assume that we know opt. Oh, first we assume that k equals 1. There's only one cluster. We're in the plane R2, so that I can make drawings. And the input is made of one ring. A ring is, so we assume that we know opt, the right point that we will call C. And we assume that every point is a distance R to C. So the instance looks like this. There's a ring around a cluster C. And we also assume that Z equals 1, so we are targeting the K-median objective. Okay. So what's the algorithm for that very particular case? Simply, we sample delta points uniformly at random. So here in that example, I have like 13 points. So I'm going to sample 2 points from them. For instance, this one and this one. And then I'm placing weights. And then, so here the weight is number of points divided by number of sample points. So that the weight of the ring is preserved. There are 13 green points, and the weight of the sample point is 13 as well. Okay, that's our algorithm, and we claim that those sample points are a Coreset. So why that? First, in expectation, the cost is the same. This is simply because every point is sampled with probability delta divided by n, and we put a weight n divided by delta. So in expectation, the weight and the probability compensate, and the cost is the same. So now we want to bound the deviation to the expectation of the cost. For that, we use Hofstadter's inequality. This says that if you have a bunch of variables xi that are independent and bounded between a and b, then the probability that the sum of the xi deviates to its expectation by x is smaller than that quantity. Okay, so we use that inequality with xi to be the weighted cost of the if sample point. So t equals delta, and we have the sum of all xi is equal to the cost of omega, cost of the coreset, by definition of xi. Now we want to show that the xi are bounded between some a and b. So our instance is made of a point c and many points at distance r to c. So if I'm looking at a center S, then the distance from any sample point and any point to S is, by triangle inequality, at most distance r, distance to go to C, plus the distance from C to S. So with the weight, it says that it means that the distance, all the xi, the weighted cost of the sample point, or the weight n divided by delta times the distance from C to S, plus r. There are at most that quantity, and there are similarly at least the distance from C to S minus r, because of the very structured input. So in that case, b minus a, the parameter here, is simply 2r times n divided by delta. Okay. So furthermore, we take x to be 2 epsilon times nr. Again, we look at the very r input, and r means is actually opt, because I said that the center C was opt, so n times r is opt. So x is equal to 2 epsilon opt, which is smaller than 2 epsilon times the cost of a to s, by definition of the optimal cost. So if I'm plugging those values into Hovding's inequality, I get this equation. The sum of the xi is the cost of omega to s. Its expectation is the cost of a to s by the first lemma. I took x to be equal to 2 epsilon cost as, okay? And then the value inside the expectation boils down to epsilon squared delta. So with that probability, S is omega is a coreset. With probability 1 minus this, omega is a coreset, because that's the inequality that's the probability that omega is not a coreset. Okay, so that was the most technical part of the talk. Hopefully it will be simpler now. Now we need to do a union bound, because we said that we're done with the first part for fixed S with some huge probability omega is a coreset. Issue is that there are infinitely many possible S. So we distinguished how, okay, question, how we deal with that. So first, if the center S is very, very far from C, meaning a distance more than epsilon, r divided by epsilon. So from S perspective, all ground points are located at the same spot. By triangle inequality, the distance from red point to S is distance from C to S plus minus epsilon times the plus minus r, which is plus minus epsilon times the distance from C to S. Okay, so that means that the cost of A to S is simply n, number of green points, times 1 plus minus distance from S to C. that's the same thing for the Coreset, omega. The cost of omega to S is 1 plus minus epsilon times the weight of omega times the distance from S to C. But by design, we picked the weights so that the weight of omega is n. So that directly means that the cost of A to the point S is equal to 1 plus minus epsilon times the cost of the Coreset to S. So this equation means that if the center S is far away, then by design our algorithm constructs a Coreset. That's the first easy case. Okay. Now in the case where the center S is close, at distance less than r divided by epsilon. So in that case we proceed as follows. We place a grid G of granularity epsilon r so that there's a grid point at distance at most epsilon r from S. Okay, and we're going to use that grid to show that omega is a Coreset. Okay, so we fix some delta, which is epsilon to the minus 2 times log of 2 times the size of the grid. The analysis we made before says that for any fixed G, with that probability, the cost of omega to G is roughly equal to the cost of A to G. So we can make a union bound to say that with probability 1/2, for all grid points, the cost of omega to G is roughly equal to the cost of A to G. This is simply doing a union bound of the previous observation. Okay, so now we need to extend from the grid to any center S. That's not necessarily in the grid. So let S be any possible center. First case is when S is very far away. This is the easy case because we just need to preserve the weight of the dataset, which is done by design. Okay, so that's the first easy case. Second case is when the distance is less than r divided by epsilon, but then we have a grid point at distance less than epsilon r from S. And then we have the following equations. The cost of A to S, so it's the sum of all distances from P to S. This bitriangle inequality is at most sum of distances from P to G plus epsilon r. But epsilon r is epsilon times the optimal contribution of P, the cost of P in the optimal solution. So this equation means that is exactly equal to the cost of A to G plus epsilon times opt. So this is smaller than 1 plus epsilon cost AG. So with the similar argument, we can say that cost of A to S is actually 1 plus minus epsilon times the cost of A to G. And similarly, we can show the same property for omega. But we know that this quantity is roughly equal to that quantity by the union bound here. So we know that those two are equal. We know that this is equal to this is equal to this here, we have equal here. And so we also have, by like transitivity of the diagram, we also have equality here. So that means that the cost of omega to S is roughly equal to the cost of A to S. So it has approximate equality, not equality in the diagram here. It's approximately equal. Okay, so for any possible center, either we are in the easy case and then the equation holds because it's the easy case, or we can use the grid to say that since by union bound the cost of the grid point are preserved, then the cost of S is preserved. Okay, so that's all for the proof. Now we need to remove the restrictions we made. So the restrictions were k equals 1 and 1 ring. The two main assumptions were that. So in the case when we have k centers, we have also log n rings because we can place exponentially growing rings. This, if we do the same analysis, we can show that in each ring here, we would need to sample order k many points. And so the total size of the coreset would be k squared log n. That's k-chain proof actually. So what we do, our contribution, is to merge rings in the analysis. So instead of considering each ring independently and build a coreset for each ring independently, we consider each ring that have roughly the same cost. So those three rings are going to be considered together in the analysis, and we show that for those three rings we need k points. So we group rings, and we show that in every group of rings we need order k points, and so that means that allows us to remove the square, because there's only log n groups of rings, sorry. Each of them needs k points, so we have k log n. Now we want to remove the log n as well. For that, we show how to discard the far rings that are very far. We show how to discard them because they actually have very few points. So we have a particular treatment for them. So we show how to reduce the number of rings. It's not log n around each center, but 1 over epsilon around each centers. So that are two ideas. Okay. And so using this, we can have a coreset of size order k times some epsilon. Now, to go beyond R2, let's think about where we used that we were in the plane in the proof. So it wasn't for okay, so actually the only place where we use it is for the grid, when we constructed the grid. So the only thing that needs to be adapted is the grid argument. So if you can show that you have some metric space and you can find a grid of every ball of radius r divided by epsilon, then our framework applies and you can build a coreset. So it's a very geometric property that's easy to state, in some cases easy to prove, as in the Euclidean, because you just need to put a grid. And this is the only thing you need to use if you want to apply our framework to another metric. Okay, so conclusion. So we give a new framework to design coreset. Simple to use because you just need to adapt that grid argument. Hopefully simple to understand. We use that framework to improve all the state-of-the-art coreset bounds in Euclidean spaces, doubling spaces, minor free metrics, etc. But that leaves a few open problems. So first, of course, can you apply the framework to other metrics? Second, for Euclidean k-means, we have coresets of size k divided by epsilon 4. We don't see any reason why that factor 4 is necessary. We believe that epsilon square isn't necessary, but question is, can you find an upper bound on this epsilon square? We have some argument to say that k divided by epsilon square is a lower bound. Can it be an upper bound as well? And for higher powers, can we have the best of the Yet for higher powers, we have two corsets, one of size k squared divided by epsilon square, or another one of size k divided by epsilon to the z plus 2. So can we have the best of the two worlds, have k divided by epsilon to the minus 1 times 2 to the order z? Don't care about that. Okay, so that's all. Thank you for listening me and watching me.